Hello and welcome back to the Countering Climate Skepticism podcast. My name is John Rainier, the history teacher, and I'm joined by my co-host Mark Prosser, the climate researcher. Thank you for joining us today. For any new listeners, each episode we tackle a different argument made by climate skeptics and attempt to debunk it. This is our 5th episode. It follows directly on from episode 4, so we recommend listening to that episode first before listening to this one. So let's get started. How are you today, Mark?
Yeah, not bad, John, not bad. I don't know if I'm having a midlife crisis, but I'm considering
Quite
getting...
possibly, yeah.
Thanks. Well, if I'm getting one, you must be getting one too, because we're the same age.
Oh, man, I've got so many grey hairs these days.
Really? You can't see it from here, but yeah. I've got grey hairs as well. Do you see them there?
Probably, yeah, loads.
Right. Okay. Right, so I am getting a motorbike, be it for reasons of midlife crisis or not. But one thing, I was telling my friend about this, and they were saying, why don't you get an electric motorbike? And I was like, oh, that's an idea. And then I sort of went and had a look around, and unfortunately, they're either too expensive or they're not good enough in terms of speed. Okay. So I've ended up, I think I'm going to end up getting a fossil fuel one. However, in my defense, it is the most fuel efficient motorbike on the market. Oh, nice. And it's like sort of 200 miles to the gallon or something like that. So
that's pretty good. But it's not really the weather for riding bikes at the moment, though, is it? It's been torrential apocalyptic rain for days up here.
Really? Is Birmingham quite wet?
Yeah. Right. Well, it is at the moment. There's been floods and everything around here.
Yeah. It's been a bit like that down here as well, but not too bad, I guess.
Yeah.
How are you anyway?
Yeah. I'm good. Been applying for lots of jobs this week and getting back into the swing of things with work after having been out of work for a year. I keep getting these notifications on my phone saying, this is where you were 12 months ago. And I'm like, stop rubbing it in. I think this time last week, we were right outside Bran Castle, Dracula's castle in Romania, spending the night there in the dark, which was quite an experience, that's for sure.
Bloody hell. Meet any vampires or?
No. In fact, it was pretty busy there. It was one of the busiest places we visited, actually. A few days after we were there, though, Elon Musk had turned up and booked out the whole castle just for himself and his mates for a party.
Right.
The life of the rich and famous, eh?
Yes. I mean, you're just behind them, obviously.
Not at all. Been unemployed for 12 months. I've got nothing. So have you had any encounters with any climate skeptics this week, Mark?
Yes, I have in the last week, but there's an interesting little conundrum that I've become aware of. So, is it a good idea to kind of respond to so-called climate skeptics on Facebook groups or not? Because because the way the algorithm works, if you respond to them, they sort of get kept at the top of the sort of the news feed.
Yeah.
And so it's interesting. There are certain people on the group that I visit about climate change that do never respond to climate skeptics because they sort of see them as trolls that just sort of feed off user engagement. So by actually trying to kind of unpick what they're saying, that's exactly what they want. It gets very warped with the way that the algorithm works.
Yeah, it's tricky, isn't it? Because I've only recently joined Twitter or X, and quite possibly the worst possible time to have joined Twitter, to be honest. And I just find the same arguments and opinions that I don't agree with, and I think it's always very healthy to hear opinions from people you don't agree with, but they just get shoved front and center because of the algorithm, and all my feed ends up just getting filled with people that wind me up because being a bit clickbaity, I've looked at what they've said. So now I just try and avoid looking. But so again, it's just not serving its purpose of actually creating a space for healthy debate because of that algorithm.
Yes, yeah, I couldn't agree more. So because of that, I've sort of stepped back from like sort of engaging with climate skeptics. But that doesn't stop a lot of other people on the site engaging with them as well. So me not engaging means that they still get, or like, you know, people who post very provocational things, you find that they tend to get a lot of attention. And sometimes even from other skeptics as well. So the skeptics keep themselves at the top of the newsfeed. So it's, Does
it count as responding if you like just drop them a little middle finger emoji every now and then? Does that keep them at the top of your algorithm?
It does, and it's what they want.
Okay.
Yeah, it doesn't upset them, John. Like much as you'd hope so. It doesn't. They love it. Like trolls are weird. You know, they kind of they like giggle when you get annoyed or put a little shit emoji.
These bloody turds. Okay, so this episode is a continuation of the episode we did previously, episode 4, looking at the Ziggurat of Denial level 2. In the first part, we gave you a grounding in the factors that have caused the warming of the last 150 years, according to climate models. You can see the research in the show notes for that episode. It's a Bloomberg interactive article. The results were that greenhouse gases and aerosols are the main players when it comes to explaining the observed warming trends, with greenhouse gases causing warming and aerosols causing cooling. In fact, were it not for aerosols, we'd have even more global warming than we have now.
Yes, indeed. It's a sobering thought. And so from that Bloomberg interactive article, which we will put in the show notes if you want to revisit it, we saw that volcanoes, the sun, land use changes, ozone, and orbital changes all did very little when it came to influencing the global temperatures of the last 150 years. Main players were carbon dioxide, greenhouse gases, warming the planet, and then aerosols cooling it slightly. Because they cooled it less than the greenhouse gases, we get a net warming, which we have seen. But despite this, the climate deniers on the second level of the Ziggurat, and just to remind people what the second level of the Ziggurat is, the first level is the Earth is not warming. The second level, people admit that the Earth is warming, but mankind is not responsible.
So for any new listeners, our Ziggurat, you can find out what we're talking about through that. We've got a separate episode available that talks about what the Ziggurat of Denial is when we're referring to that in the episode.
But despite this, climate deniers on the second level of the Ziggurat either play down the carbon dioxide greenhouse gas explanation, or they play up one of these other factors, the sun, volcanoes, etc. So in this episode, we will look at two of these alternative explanations. It's the volcanoes explanation for climate change, or it's the sun, and hopefully convince you that neither of these alternative explanations could be true. Okay, so moving on to the first of explanation. It's the sun that causes climate change. So first of all, it's important to note that the sun has and has always had a large impact on Earth. And it's the reason that if the sun wasn't shining, Earth would be minus 270 degrees. So the fact that we're 15 degrees is because the sun is there shining. So it has a huge effect on the Earth. And so in this sense, it's probably unsurprising that skeptics reach for it as an explanation for the global warming that we've seen over the past 150 years. And the sun does fluctuate, over an 11-year cycle. However, if you recall from the Bloomberg interactive article of last week, it doesn't really fluctuate enough to have much impact on the climate overall. Let's just take a quick look.
So this is on the Bloomberg article, is it, we mentioned?
Yes. So we looked at this figure and like other aspects that influence the climate last week. But this, so just to remind viewers of what we've got and what we're seeing in front of us, we have this time series of it's 125 years, 1880 to 2005, and then you have the observed temperature in black, and over time that sort of increases until the modern day. And then you have they have a line which sort of tends to sort of wobble around zero, but has small perturbations up and down, but doesn't really. It's sort of almost like a flat line, and it is the contribution of the changes in the sun to the observed trend in warming.
Okay.
And so while you do get, like, for example, in sort of about halfway through the time series, you do get a slight increase. It's still far smaller than you'd need to explain the observed trend in carbon dioxide.
Yeah.
However, rather than just telling you that the sun's impact is insignificant on the warming we've seen in the last 150 years and leave it at that, I'm going to give you 4 reasons why the global warming we have seen can't be due to the sun and is highly consistent with an increased greenhouse gas effect. So, John, I might be putting you a bit on the spot here, but what's your understanding of how the Earth is warming up with global warming? Sorry, a bit of an open-ended question, but...
So I think it's that the sun's rays enter the atmosphere. Some of them are absorbed by the surface of the Earth. Some are reflected off the surface of the Earth back out to the atmosphere. But whereas normally they would some of them would escape back out into space, because of global warming, they're now trapped within the ozone layer, is it? And then reflected back to Earth, causing warming.
That wasn't too bad an explanation at all. The only thing... So I would say that it's not the ozone layer that's sort of preventing them from escaping. It's the sort of the carbon dioxide in the atmosphere.
Okay.
But essentially, I think you've got the main point. So essentially, what's funny about the sun's rays is that they're in the visible portion of the light spectrum, and because of that, they can just zip through the atmosphere without having, as if it's a transparent sheet of glass. And then it hits the surface, or it hits the sea surface, it warms it up. This then, the sea surface or the land surface, then re-radiates infrared radiation. And then this is the radiation that kind of gets blocked by greenhouse gases.
Okay.
And so they don't necessarily get reflected back down. They could be reflected sideways, but it just tends to sort of slow down the exit. So eventually it gets out, but more of it is kind of blocked, if that makes sense. But your answer was pretty decent.
Okay.
Piece of evidence number 1. When we say that the atmosphere is warming with climate change, we are only referring to the lower atmosphere. To simplify a little, the atmosphere that is lower than the height that commercial planes fly at. So we're not talking about the atmosphere above planes, basically. And this is because the atmosphere above planes has seen a cooling trend over the last 150 years. So whereas below that altitude, there's been a warming, above that altitude, there has been a cooling.
Okay.
So this is kind of a little bit counterintuitive, I guess. Like, is it counterintuitive for you, or does that surprise you, or is that not so surprising? Or
it does, I guess. Is it maybe that it's because the trapped heat by greenhouse gases means that less sunlight's reaching the upper atmosphere, so therefore it's cooling?
Exactly. That is spot on. The reason why that's happening. So I did have a graph to show this. I think I'll just put it in the show notes rather than show it to you now. But yeah, that's exactly what's happening. So you're getting less radiation sort of being beamed up from the Earth, reaching the stratosphere, and therefore it's been cooling. If the sun getting hotter was the cause of global warming, then we should expect the whole height of the atmosphere to get warmer, and not just the bottom.
Yeah.
So that's the first bit of evidence pointing towards carbon dioxide being the reason and the greenhouse effect rather than the sun. For the remaining 3 bits of evidence that I'm going to give you, explaining why it's not the sun, I want to explain something first about the climate, and in particular why we sometimes refer to it as a climate system. Any idea why we might refer to it as a climate system? Or
is it the fact that it's a process with several parts to it, rather than, to show my real unscientific terminology here, rather than being a fixed thing?
Yeah. That's there's truth in what you've said there. I guess it's a little bit vague,
and
but
also a lot of bollocks. Yeah.
But no, I put you on the spot, so So let me explain a little bit what I mean by a climate system. So if you imagine for a second, John, a big bathtub with a tap or a faucet at one end, and because this is a slightly fucked up bath, we're going to have the hole where the water drains out at the opposite end of the bath.
Okay.
If we turn on the faucet, what happens to the bath?
Well, I presume, unlike in a normal bath where the water would just drain out the plug hole straight away, I imagine it would take a little bit longer for the water to drain out. So it starts to fill up a little bit, but then does start draining out slowly over time, but once it reaches the other end.
Exactly, yes. So I guess this bath is an example of a system, and this is how I kind of perceive a basic system. You have 3 elements. You have the inflow of water at the top, and this can be at varying rates. You have the reservoir, so the amount of water that's in the bath itself, and then you have the outflow at the other end through the hole. So the Earth's climate system is kind of pretty similar to this in a way, but instead of it being water, it's energy. So the sun beams in energy to the climate. You then have a certain amount of heat energy in the Earth system itself, and that's why we're on average 15 degrees. And you then also have an outflow of heat that is lost to space. Is that relatively straightforward?
Yeah, sure.
Okay, so the equator, the season of summer, and days as opposed to nights, have something in common, as do the poles, the season of winter, and nights. The equator, summer, and days are all places and times where heat energy is lost from the climate system. Much like areas immediately under the faucet in our bath, at the equator, at summer, and during the days, energy is accumulating in the system, or water is accumulating, and over the plug hole, it's a bit like the poles, winter and nights, energy is being lost from the system. Do you have any idea why the equator is warmer than the poles, John?
Is it due to the curvature of the Earth? So the equator is closer to the sun than the poles are?
So you're correct that it's to do with the curvature of the Earth, but it's not really correct in the sense that it's the distance from the sun. Okay. And so this is I think this is what everyone thinks until they learn otherwise. But it's actually to do. Okay, so if you imagine I have a torch here, and I'm shining it on a flat surface, you get like a circle of light will appear on the cardboard.
Yeah.
and that's quite kind of concentrated beam of light. And if I then take the piece of cardboard at the same distance away from the torch and I tilt it to 45 degrees so that some of the cardboard is closer to the light and the bottom part of the cardboard is closer to the light and the top part is further away, you get a kind of an elongated circle, don't you?
Yeah, yeah.
And so the area of this elongated circle is maybe about twice as large as when the cardboard was directly in front of the torch. So this means that the energy in the light has had to be spread over twice the distance, twice the area.
Right.
And
okay.
so that makes it like less powerful.
Okay. Yeah.
So for example, if like if you're somewhere in America during the heat of summer and the sun is like right above you, it's bloody hot,
Yeah.
right?
Yeah. Yeah.
But if you're sort of standing somewhere when the sun's about to set, the sun is still there, it's still the same distance, but it's just not very powerful.
Yeah. Yeah.
That's because you're basically on a piece of cardboard that is inclined at an angle such that the sun's rays are having to cover.
They're dispersed over a larger area. Yeah. Okay. Oh, that's interesting.
Yeah. It's something that like not a lot of people know, but it's not. So one of the funny things is that I think we're actually, because of the orbit of the Earth, I think we're actually kind of closer to the sun in winter.
Because that's the thing that did confuse me, because like you say, because of the tilt of the Earth as well, there are points in the year where we are in our summers closer to the sun rather than further away. But I presume it's also because it's factoring in the angle of it as well. Yeah,
I think basically I don't think it makes the distance closer we are to the Earth, to the sun. Is not very significant. So it would make us maybe a tiny bit colder or warmer, but it's not the main difference. The main reason is the sort of the angle that the sun's rays hit us at.
Okay.
Yeah. And in winter we're actually a little bit closer to the sun because the Earth doesn't orbit in a complete circle.
Okay.
So given that understanding that I've just explained, if the sun was getting hotter and warming up the planet, as it would do if the sun was actually warming up, the planet would heat up. Which would you expect to heat up faster, the equator or the poles?
I'd probably expect neither. I'd probably expect it to happen equally, because I imagine the speed of light would make the differences negligible.
Sure, but so if you can sort of go back to the torch and the cardboard expression, the equator to visualize this.
Okay, so you would expect the equator because there's less of an angle on the equator, so there's more concentrated light hitting that area.
Exactly, yes. So both the pole and the equator would heat up, but the equator is getting that concentrated beam of sunshine, but the pole is getting pole is usually far more slanted compared to the equator. The equator is typically always like that flat piece of cardboard, sort of perpendicular to the sun's rays. So you would expect the equator to warm up faster than the poles. However, we don't see this with climate change. We see the opposite. Global warming is currently happening twice as fast at the poles as it is at the equator. Very strange. Any thoughts on this, John, at this juncture? Or
yeah, I mean it's really interesting that it's happening that way around. Like, is it something to do with like the changes being more noticeable at the poles? So obviously, like when temperatures increase from either side of the freezing point of water, is it that we see a very dramatic and very obvious effect there, that when ice melts it seems like a more obvious change in temperature than it would be elsewhere?
So not really, no. It's so for example, if we've had a certain rate of warming generally, so I can't remember the precise, so if we say like 0.2 degrees per decade, I think is the kind of the average global warming. So every decade we get 0.2 degrees warmer. So at the poles, it's been getting 0.4 degrees warmer per decade, or something like that. Don't quote me on these figures, but they're roughly about right. So if we go back to the metaphor of the bath here, the poles are on average a bit like the drain hole, where heat is lost from the climate. So the fact that the temperature is going up there means that heat must be accumulating, which seems to suggest that there is something clogging up the drain hole, making it smaller perhaps, such that the poles are warming up faster than the equator. Do you have any idea what on earth might be causing this, John?
Is that where the hole in our ozone layer is?
So there is a hole in the ozone layer, but I guess maybe I should speak to at this point. I think a lot of people tend to sort of mix up the ozone hole problem with climate change. So we have up in the stratosphere, so 20, 30 kilometers high, we have a lot of ozone. And ozone helps to block out ultraviolet light, which or sort of stronger versions of UV light, which can cause cancer in living things. And because we have been using certain CFCs, these CFCs chemically react with ozone and take it out of the atmosphere. And so because of that, we've had an ozone hole developing in the atmosphere. And this is kind of quite a separate problem to climate change. They're largely separate. And for example, if we got rid of all of the ozone layer across all of the Earth, it would be very difficult for biological life to exist without getting cancer, basically, because a lot of the rays from the sun are very high powered, and if the ozone layer didn't absorb them on our behalf, we would get cancer. And before the ozone layer existed on Earth, I think most life did exist underwater, because that was the only place it could really exist. So climate change is, we stick greenhouse gases in the atmosphere, and that basically means that the planet can't cool down in the way that it used to, and that means that we get hotter and hotter. So yeah, do you see how they're different as problems?
Yeah.
Yeah, I mean, it's you're not the first, John, and you won't be the last. I think a lot of people, because that was the first environmental problem that really hit public consciousness.
Yeah.
But climate change.
I remember watching Blue Peter as a kid and learning about it.
Really? What was it? Was it Blue Peter? When did you watch Blue Peter?
When I was a small kid, Mark.
Yeah. But was that? I remember watching Blue Peter when I was 6.
Yeah.
Oh, so it was. Oh, okay. Maybe it was.
Well, I think it was around in the 90s, wasn't it?
Yeah. Okay. All right. We digress.
That and acid rain, those were the big things, weren't they? Acid rain and the ozone hole.
Yes. And climate change wasn't really on our radar until a bit later, right? So I guess the point I was trying to make is that sort of heat is sort of accumulating at the poles and warming it up. Sorry, heat is accumulating at the poles. So heat comes into the climate system at the equator. This then warms up the planet. The climate redistributes this heat to the poles, and then it loses that heat to space. That's typically the way that. So in the case of the bath, water comes in, water goes out. In the case of the climate, heat comes into the equator, gets redistributed towards the poles, and then gets lost at the poles. But the poles are heating up, and this is because sort of heat is sort of accumulating there, and it's not able to get out as fast. And so this is because of greenhouse gases accumulating in the atmosphere, meaning that the pole is less efficient at losing this heat to space. And I don't know if this will help clarify things a little, but if you go to the planet Venus. Do you know anything about the planet Venus, John? Or
It's really bloody hot.
Yes, that is true.
Because of the CO2 in the atmosphere.
Oh, very good. Yeah, it's got an atmosphere that's like almost 100 times larger in mass than ours, and that's despite being on a planet that's like about the same size. And the atmosphere is just, I think, 97% carbon dioxide. So it's not, 420 parts per million. It's like,
No.
it's just a tiddly amount compared with Venus. But yeah, so it's surrounded by this incredibly dense atmosphere of carbon dioxide, and because of that, you find that the temperature at the poles is almost exactly the same as the temperature at the equator. So basically, heat almost can't get out of Venus. It can come in, the sun can beam it in, because the visible light, CO2 is transparent to visible light. It warms the surface, it then almost can't get out because it's just smothered by such a thick, dense atmosphere. So if you increase the greenhouse gases indefinitely, what you'll find is that the temperature at the poles will try to catch up with the temperature at the equator. So at the moment, the temperature of the poles on Earth might be something like, it might average like 25 degrees or 30 degrees. And then at the pole, it might average -5. So there's
is that like when when you have like air temperatures, they kind of equalize out, or water temperatures equalize out over time when they're mixed? When you mix like hot air with cold air, they try and equalize, don't they?
Yeah, I suppose so. Yeah, I mean, but you've got to remember that the equator and the poles are sort of quite far away.
Yeah.
So, but yeah, in effect, you're right. So if you reduce the ability for any heat to escape from the planet, then essentially it's a bit like if you close all the doors and windows in a room and put on the air conditioning or the heating, then fairly soon, because you've stopped any heat escaping, it won't be a case of like the area near the radiator will get hot, but some other area like way across the room will be cold. If you leave it for long enough, then eventually it'll all become the same temperature. If you've closed all the windows and closed all the doors. Okay, so we've given you two bits of evidence against the idea that it's the sun that's causing climate change. The first is that we're seeing warming in the lower atmosphere, but we're seeing cooling in the upper atmosphere. This wouldn't be happening if it was the sun. The second piece of evidence is that if it was the sun, you'd expect the equator to be warming up faster than the poles. Whereas in reality, we see that although the poles are still cooler than the equator, they're warming at a faster rate than the equator is. So the poles are seeing a faster rate of change than the equator. So the third and fourth piece of evidence are a little bit similar to this equator and the pole argument. With climate change, we notice the following two phenomenon. Third piece of evidence, we see that winters are warming faster than summers. The fourth piece of evidence, we notice that nights are warming faster than days. Any comments on why this might be, John? Or
not a clue.
Okay, so essentially you have it's a bit like the equator and the pole argument. So you have a place in the system where heat is coming in, and you have a place time where heat is being lost back out. And if a warming sun was the explanation for climate change, we'd expect summers to warm faster than winters and days to warm faster than nights. Because you'd be having, if it was the sun, you'd be having extra heat come into the system. And because days and summers are when heat comes into the system and warms up the system, then you'd expect them to warm up preferentially rather than the poles.
Okay.
or nights or winters. But you don't see that. You see nights and you see winters warming up faster than the equator or summers or days. So this again is because the greenhouse effect, it doesn't matter if it's night or day or winter or summer. It's 24/7, and the Earth is constantly trying to lose heat at nights, at the pole, at winters. But if it's sort of covered with a sort of a layer of increased greenhouse gas concentrations, it's going to struggle to do that. And so that would lead to, if you stop it, if you stop its ability to lose heat to space, heat is going to accumulate there in nights, at the poles, in winters.
Okay.
And that's going to drive up the temperatures faster than in summer, in the equator, during days.
Okay.
Does that sound convincing, John?
Yeah. I mean, that's a pretty convincingly debunking the sun being responsible for this.
Yeah, I think so. So essentially, it's you don't particularly have to rely on sort of arguments about the sun's out. You could look at data sets which look at how much the sun has been changing its output, and so that's one way you can sort of look at the problem. Well, there hasn't been a large change in the amount of energy that the sun has been producing. But this is more like, well, if you just look at global warming, you might think that everywhere is just warming up at the same pace, but it's not. There are interesting differences, like we've talked about, like the poles are warming much more quickly than the equator. Nights are warming faster than days, and winters are warming faster than summers. So this pattern of warming suggests that it can't be the sun, because we'd expect the opposite to be the case if it was the sun.
Okay. So I guess our next skeptic argument then is looking at the volcanoes and the idea of people arguing that volcanoes must be responsible for climate change.
Yeah. So before we start, just to draw your attention to this, this one is a little bit different to the sun argument, because with the sun, we were making our arguments about heat. For this next argument about why it's not volcanoes, we are moving away from heat and focusing instead on carbon dioxide to make our logical argument about why it can't be volcanoes. First of all, John, do you have any idea why some skeptics might want to argue that the recent warming that we've seen could be driven by volcanoes, or any idea how volcanoes might affect the climate more generally?
Well, I guess skeptics, from what we've seen from some of the arguments they've been making, want climate change to have a natural cause. So volcanoes seem to be a great example of a natural hazard that would mean that they don't need to do anything differently. I think volcanoes, from my understanding, they put a huge amount of dust and ash into the atmosphere when they erupt, which I think can trap heat. When we were in America, we visited Mount St. Helens, which had a very famous eruption in 1980, an eruption so massive that the entire state of Washington was put into a state of emergency. And the dust cloud apparently was so massive. One of the guides there was telling us that they'd had a tourist come and visit, and they'd come from Germany, and they'd said that the factory that they'd been working at in Germany had to close for a couple of days shortly after the eruption, because the ash cloud from the eruption on the other side of the world had then got into the air filters in the factory, and it wasn't safe for them to operate. So I think volcanic eruptions, people have seen that big volcanic eruptions can have a massive impact on the global climate. Yeah,
that's true, and certainly the large ones in history. So when was this eruption? What
that was 1980. It was
right.
The largest landslide caused by a volcanic eruption in human history, in recorded human history. So it was so massive that like about 300 foot off the top of the mountain disappeared. One whole side of the mountain just completely blew out. So it's quite a dramatic eruption.
Damn. Yeah. I mean, there's no getting around it. Volcanoes are, powerful things, and like, if you get a really powerful one, even going back before 1980, if you go back to some of the really big eruptions, they can affect the climate. Because if they explode hard enough, they can get stuff into the stratosphere, and usually volcanoes are kind of associated with cooling the planet. So it's rather than warming it, it's cooling it, because they emit these particles called sulfate, and sulfate tends to reflect away sunlight. So you get sunlight coming in, these little twinkly bits of glitter up in the stratosphere, which stay there for ages, tend to reflect away sunlight. So you actually get a cooling. But skeptics are arguing that volcanoes might warm the planet, and this is because volcanoes also emit a large amount of carbon dioxide when they erupt. And so the climate myth is that volcanoes emit more CO2 than humans do. And as with all good myths, it contains a slither of truth. Volcanoes do emit CO2, and the exact amount is subject to a bit of debate. But that being said, all available estimates indicate that the amount of CO2 is probably 100 times less than man-made emissions of CO2. Like at least 100 times less, maybe 300 times less. So, but then again, we can do far better than just simply saying that and say, trust us. We can demonstrate conclusively to you that the CO2 that we have in the atmosphere, the extra CO2, we went from 280 parts per million to 420 parts per million. This extra bit, we can kind of demonstrate that it isn't from volcanoes. And I find this series of arguments really quite clever indeed. We've got an extra 50%. The atmospheric CO2 level has been increased by 50% since the 1850s. But for now, let's keep an open mind about where this all comes from. And let's posit 4 different possible explanations of where this CO2 has come from. So explanation number 1, it came out of the ocean. 2, it came out of volcanoes. 3, it came from some recent biological source.
Like cow farts.
Like cow farts, yeah. Yes, and they are indeed an issue. But not for carbon dioxide, but for methane.
Yeah.
But and then the 4th one is ancient biological sources, like fossil fuels, because fossil fuels are bloody ancient. They're tens to hundreds of million years old. Made from creatures that sort of lived and died hundreds of millions of years ago. So, if I recall correctly, you didn't stick around for AS chemistry, did you, John?
I couldn't get my head around it at all. Did it for a couple of weeks, didn't know what was going on, left.
Do you remember like protons and neutrons and stuff like that?
Oh yeah.
Like, could you tell me how many protons a carbon atom has?
Oh, actually, I think I might know this one. Yeah,
Ooh,
so
right.
I taught a GCSE science lesson this week, so
right.
That's been well timed, doesn't it?
Oh yeah.
Right. So what do I need to know? What's the atomic number of carbon and the atomic mass? Is the atomic number 14?
So you're saying the atomic mass?
I seem to. Is the atomic number tells you the number of protons, and the atomic mass tells you the number of protons and electrons combined. No, the number of protons and neutrons combined, because electrons don't have a mass.
Correct. That's bang on. So for carbon, do you remember the atomic number, or what number in the periodic table is it? What element number is it?
Is it 14?
So no, it's number 6 actually.
Oh, is it? Oh, okay. I'm way off.
Yeah, but I mean, the atomic mass can be 14.
Oh,
but
okay.
usually, so usually you've got 6 protons.
Yeah.
So it's hydrogen, helium, lithium, beryllium, boron, carbon, and nitrogen,
Okay.
oxygen. So it's number 6. So it's got 6 protons, and typically it has 6 neutrons as well, which gives it an atomic mass of 12. So the majority of the carbon in the ocean, in the atmosphere, in the environment more generally, is carbon-12. So like 99% of it is carbon-12. 6 protons, 6 neutrons. And this is called, so when you say carbon-12, you're talking about an isotope. And did you teach what isotopes were? Or
Yeah, so isotopes, so different versions have the same atomic number, so they've got the same number of protons, but they sometimes have different numbers. Isn't it normally electrons? They have different numbers of electrons.
No, neutrons. So the proton tends to always like match the number of electrons, because protons are positive, electrons are negative, so they tend to cancel out. But the different number of neutrons makes it a different isotope.
Okay.
So yeah. So 99% of it is carbon-12, but 1% of all carbon in the environment is carbon-13. So that has 6 protons and how many neutrons?
4 carbon-13, so that's 7.
Correct, yeah. And then there's another isotope of carbon called carbon-14, which is just a tiny, tiny, tiny fraction of all the carbon in the environment, and it has 2 extra neutrons.
Okay.
Couple of quick questions, John. What elements are plants and trees mostly made of?
Carbon.
Mm-hmm. And where do they get this from?
From the soil.
So they don't actually. They get it from the carbon dioxide in the atmosphere.
Oh, okay. So through photosynthesis.
Yes. Yeah. So if you remember, photosynthesis, they take on the left side of the equation, they have carbon dioxide and they have water. And as long provided plants have these 2 things, they can then make glucose and oxygen. And so that's why trees give us oxygen. But yeah, essentially, people tend to think like plants get there. So the bark that you see on a tree isn't from the soil or brought up from the soil. It's essentially the tree kind of like breathes in the atmosphere, the carbon dioxide that's in the atmosphere, and then incorporates this carbon dioxide into itself.
Okay.
So that's how kind of trees work in a nutshell. In a particular coincidence of nature, plants kind of dislike carbon-13 and carbon-14, so these heavier isotopes of carbon. And so they preferentially take up carbon-12. So this means that instead of 1% of plants being carbon-13, the actual amount, if you take a stick of celery, is going to be more dilute than typically in the environment because they're picky eaters, kind of.
Mm.
So now, given that coal, oil, and gas, fossil fuels, are made up of dead plant matter that is millions of years old, what do you think will happen to the ratio of carbon-12 to carbon-13 in the atmosphere over time if we burn an enormous amount of fossil fuel, as we have done?
I presume it would release a lot more carbon-12 into the atmosphere, so the ratio of carbon-12 to 13 would increase.
So the ratio, hang on, get this the right way around.
There'd be more carbon-12 going into the atmosphere if we're burning fossil fuels.
That is correct, yeah. So basically carbon-13 would become more dilute, basically. Yeah. Correct. So there's a graph which you can see, and I'll put this in the show notes if anyone wants to look at it. So it looks at the amount of, or the ratio over time and how that's dropped. So crucially the carbon carbon-13 that comes out of a volcano is not dilute. So there are no picky plants involved there. So if it was volcanic CO2, we would not expect the dilution of carbon-13 that we have seen in the atmosphere. But here, a skeptic might butt in and say, but hang on, you had like 4 potential explanations. You might have ruled out the volcanoes as an explanation. But what about carbon coming out of the ocean? What about more recent biological sources? Sorry, just to quickly explain, like carbon coming out of the ocean. So the reason why this is a potential explanation is because the ocean contains within it a certain amount of carbon dioxide that's dissolved. And as it gets warmer, this carbon dioxide, it can't hold as much carbon dioxide as when it was colder. So colder water can hold more carbon dioxide. So as it gets warmer, you might get carbon dioxide released from the ocean. So the skeptic might make this argument there. You haven't ruled out all 4 of your explanations. You might have ruled out volcanoes, but what about the other 2? So here we move on to carbon-14. So carbon-14, unlike carbon-12 or carbon-13, is radioactive. It is created when cosmic rays react with nitrogen in the atmosphere. Nitrogen is the biggest gas in the atmosphere. And it turns it into carbon by some sort of reaction. Do you happen to remember from maybe GCSE physics about what happens to radioactive isotopes over time, John?
They have a half-life, so they're constantly. I think is it that they're releasing electrons, is it, or they're releasing one part of themselves, which causes the half-life?
Yeah, so I at the moment the details of what exactly happens elude me, but yeah, you're right. There's some sort of decay that happens, and crucially, if you have like 100 atoms on day 1, and you have a half-life of 10 years, then after 10 years, only 50 atoms will remain of this radioactive nuclei. And then if you have another 10 years, another half-life, only 25 of them will remain. So the half-life is the amount of time it takes for half of the radioactive nuclei to disappear. Does that make sense? Do you remember that?
Yeah.
So in the case of carbon-14, it has a half-life of 6,000 years. So it takes 6,000 years for half of them to disappear. And fossil fuels are millions upon millions of years old, sometimes even hundreds of millions of years old. You'd expect that all of the carbon-14 would have disappeared in them. So what do you think is happening to atmospheric carbon-14 if we burn a lot of fossil fuels, John?
Is it getting diluted?
Yes, it is. And we've got another figure here, which we'll put in the show notes, that shows this dilution of carbon-14. So this then tells us that the source of our carbon dioxide in the atmosphere that we're attempting to explain is the source of it must be very, very old. Because if it wasn't very, very old, you wouldn't be getting this dilution effect of carbon-14. So this immediately rules out CO2 coming out of the ocean or more recent biology. So just to recap, the carbon-13 isotope told us that the carbon was from an organic source, so plants or animals, because plants are picky with how they incorporate carbon dioxide into themselves, and not from an inorganic, just a merely chemical reaction source like volcanoes. Carbon-14 told us the extra carbon in the atmosphere must be from a very ancient source, which ruled out newer sources like carbon coming out of the ocean or more recent biological sources. So what explanation is left to us, John?
That burning ancient biological sources of carbon, for example, coal, oil and gas, are the only possible reasons why CO2 levels have increased in the atmosphere.
Yeah, it's the only explanation left, isn't it? Yes. The extra carbon that we're looking for must be both biological and ancient. Fossil fuels seem to fit the bill where nothing else does. However, there's even more evidence that the extra carbon isn't from an inorganic source like volcanoes. So, apart from carbon, what other element do you find in CO2, John?
Oxygen.
Correct, yeah. So if we burn a shit ton of coal, oil and gas, what would you expect to happen to atmospheric oxygen levels?
That the ratio of oxygen to CO2 would decrease, their relative percentage would decrease.
You'd find a decrease in the amount of oxygen in the atmosphere, because simply taken, you take an oxygen, or you take two oxygen to oxidize with a carbon atom to make CO2. So every time a carbon gets burnt, oxygen is sort of drawn down from that. So yeah, so you get a decrease in the amount of oxygen. And we have another link here which can show you that effect in the show notes. Now, a reduction in the amount of oxygen in the atmosphere does sound alarming, but don't worry, the oxygen is in no danger of running out, as there's just so much there in the first place. Remember, oxygen is 21% of all of the gas in the atmosphere, and CO2 is just less than half of 0.1%. But this measurable phenomenon of the oxygen decreasing wouldn't be happening if it was due to volcanoes. The source has to be biological and old. Fossil fuels are both biological in origin and tens to hundreds of million years old. What do you think, John?
We're all fucked. Might as well just carry on as we are.
I thought that would be an optimistic, we're able to see past the skeptics' argument. We're able to show that it can't be volcanoes, but yet that leaves you glum and depressed.
No. I think everything else is leaving me climate depressed. Maybe it's time to move on to our good news story. So this week's good news story is about the ban on single-use plastics. So this is a ban that came into force in the UK in October of 2023. It involves a ban on all single-use plastic plates, trays, bowls, cutlery, and some polystyrene cups. So apparently in the UK, we use 2.7 billion items of single-use cutlery every year, and 721 million plates are used in the UK every year. So this is going to have quite a significant impact on the use of plastic. Only 10% of these are recycled each year. So apparently worldwide, 300 million tons of plastic are produced each year, of which 14 tons end up in the ocean, making up 80% of ocean litter. So although I'm sure this is only a small fraction worldwide, at least it is the beginning of a reduction in plastic waste that is just not needed, and can be replaced with something that can at least be recycled.
Yeah, that definitely is good news. Every time I see plastic knives and forks, there's an inner scream in my head. It's just the fact that it's been allowed to carry on, for so long, it's just ridiculous. So I'm really happy about that.
Yeah, absolutely. And I was quite surprised that statistic about how much we still use, because I have to admit I haven't really been seeing that much single-use plastic. When I buy food, when you buy takeaway food, it was really noticeable when we went over to America and ordered a few takeaways, just how much stuff was still in single-use plastic, and that's what made it stand out to me that we've been making a really big step towards this. Apparently, this law was announced back in January, so I think there's been a phasing out over the last 10 months of the use of single-use plastic. So maybe we've been seeing the impact of it already. And it's quite reassuring as well that like Wales, Scotland, they got in there first. They beat us to it in England, and it seems like it's quite a consistent approach that's going across the EU as well. That most of the EU and the UK are phasing these things out quite rapidly. Almost, it seems, in a bit of competition to beat each other to be the first ones to do it, which is good.
That's great. Yeah, I mean, like, just in general, I care a lot about climate, and I don't fly and don't eat meat and these sorts of things. But in regards to plastic, every time I go to the supermarket, I come back and it's just like tons of plastic, which goes in the recycling, but you don't know if it's going to actually be recycled. And but I suppose to a degree that supermarket plastic is inevitable, but at least get rid of the stuff that we literally don't need to use, like single-use knives and forks.
Absolutely. And like, just as a bit of a shameless plug to a local business nearby us. So there's a company called the Clean Kilo, and they introduced their whole remit for a store is selling products that are not in plastic. They're a zero waste shop, which is really good. They've got one branch. I think they might still have one in the city centre in Birmingham, but they've got one in Bourneville. They've got one somewhere else. I'll see if I can find out. Should have looked that up before I started talking about them, really, shouldn't I? But yeah, they're a great shop to get along to, and really sustainable. Lots of vegan things available there as well. But basically, you bring along your own bottles and things like that to fill up your food, which is just great fun. Takes a bit of time, but once you get into the routine of shopping there, you can get pretty quick at getting around the store and weighing all your products. So yeah, definitely recommend popping in there if you're local.
Yeah, we'll stick a link to that in the show notes, I guess.
Yeah. Next episode, we're going to continue looking at arguments related to the second level of the Ziggurat, arguments that climate change is not man-made, and we're going to be debunking the ideas that climate change is not caused by carbon dioxide. If you want to know more about the Countering Climate Skepticism podcast, check out our website at ccspod.podbean.com. If you've enjoyed the episode and would like to support the show further, you can leave us a review on iTunes or Apple Podcasts. So goodbye from me, John Rainier.
And goodbye from me, Mark Prosser.
And our final quote to leave you with today from George Bernard Shaw: "Progress is impossible without change, and those who cannot change their minds cannot change anything." Thank you for listening. So that's it for this episode. Oh, fuck's sake.